Okay, this lesson is on graphs of rational functions. So we have already talked about simplifying rational expressions, adding, subtracting, multiplying, and dividing. Now we're going to actually look at what expressions in a rational form actually look like in terms of graphs. So it's super important to talk about end behavior when we're talking about rational functions because we typically see patterns and predictability in the graphs of rational functions just by looking at the equations, and we learn information about end behavior. So just to review, we talked about end behavior actually in chapter 1. It was a part of your summer work. We talked about, let's say we had a graph like this, and we talked about end behavior using limit notation. So that's what we'll do right here. And we used limit notation by writing LIM for limit of f of x. And in this case, if let's say this is our function f of x, and we want to look at the function value or the y value as x approaches infinity, because that's what's happening at the end of the graph. So as x gets larger and larger and larger approaching infinity, in this case, we see that at the end of this graph, the graph is going to get closer and closer to 0. So in this case, that limit would be 0. And then we'd also look at what happens at the other end of the graph as x approaches negative infinity. So the limit of f of x as x approaches negative infinity, again, so as x is getting smaller and smaller, and on the left, this end of the graph, it's always which y value is it approaching, and this is approaching 0 as well. So this should be a review of end behavior, what that means, and limit notation to describe that. So we will be using limit notation. Now, one thing that is new is talking about what happens locally on a graph. So we still use a limit notation to describe this, but when we talk about local behavior, for example, in this example that I have here, if you notice what happens when x is 0, the function does two different things. So there's something worth noting happening at 0. So we describe that using local behavior. So in this case, we talk about the behavior of the y value to the left and right of a specific x value. So in this case, that x value is 0. So in this case, I would say the limit of f of x as x approaches 0, I'm going to keep it general here because like this, our specific x value is c. I'm just going to say as x approaches c. And to specify which side you're approaching c from, either the right or the left, you use either a plus or a minus symbol. So that little c plus, that plus means it's being approached from the right-hand side. So if we did this as x approaches 0 from the right, this is as x approaches 0 from the right, the function value is approaching negative infinity. And then you would also talk about the local behavior from the other side of c, in our case 0. And you just use a little minus sign after it. That indicates it's approaching 0 or c from the left. So then you would say, okay, what's happening to the y value there? It's going up and up and up, so that would be infinity. So this is what local behavior looks like. It's still using limit notation, but instead of x approaching positive and negative infinity, it's approaching a specific x value from the right and from the left. So these next few examples are just going to help us get into practice of describing end behavior and local behavior. So in each of these next 3 examples, we're going to sketch the graph. We're going to use limit notation to describe end behavior and local behavior, and then talk about the vertical asymptotes. So in this first example, 1 over x squared, I would definitely encourage you to pause the video, graph it on your own graphing calculator just so that you guys are getting that regular practice, and sketch a graph in the box. Okay, so as you sketch it, here's my axes, and you should see, hopefully on your own, that the graph of this function looks like this. So there's a sketch of our graph. Now, when we describe the end behavior, again, we're talking about the ends of the graph. So as x gets really, really, really big and as x gets really, really, really small. End behavior is always at the ends of the graph. So end behavior. To describe the end behavior, we will use limit notation. So the limit of our function f of x as x approaches infinity. So if we look as x approaches infinity, our function value looks like it's getting closer and closer to 0. If you graph it yourself, you can see that yes, it is getting closer to 0. And we also see that it's getting closer to 0 as x approaches negative infinity as well. So we can write plus minus infinity, and it equals 0 for both of those. So that is our description of end behavior using limit notation. So now moving on to local behavior. When you're talking about local behavior, first you have to figure out what value of c is the interesting value to be talking about local behavior. And in this case, that value of c is going to be right here where there's kind of a gap in the graph. So we're interested in this local behavior, which happens at, in this case, x equals 0. So to describe that, we're going to talk about what happens as x approaches 0 from the right and from the left. So the limit of our function as x approaches 0 from the right, so that little plus sign goes up above to the right of the 0, that indicates we're first just looking at as x approaches 0 from the right. Here's 0, here's the right just to the right of 0. So as x approaches 0 from the right, the function is going higher and higher, which means it's approaching infinity. Then we're going to describe that local behavior from the other side, or the left, so as x approaches 0 from the left. So we'll put a little minus sign there. And in this case, from the left, it's also approaching infinity. And then this last part, the vertical asymptote here, you guys need to brush up a little bit on writing equations of vertical lines. So this vertical asymptote here takes place at x equals 0. So any vertical asymptote is actually an equation that looks like x equals some value. So our vertical asymptote is x equals 0, which happens to be the same value of our local behavior area of interest, which is where x equals 0. All right, so let's take a look example here on the next page. Again, I would encourage you to pause the video, graph this on your own calculator, sketch a graph, and resume play. So once you go ahead and sketch a graph of this, you should see that the function looks, let me get some values on my x-axis. All right, so our function looks something like this. So that's my sketch, and now I want to describe the end behavior. So that's what's happening at the ends of the graph where x gets very, very, very big or very, very, very small. We can see from the graph and from a table, if we wanted to just be sure, that this graph is approaching 0 as x gets very large and as x gets very small. So similar to our last example, we can write that the limit of g of x as x approaches positive and negative infinity is 0 on both ends. Even though it's approaching 0 from below here and from above here, it's still getting closer and closer to 0 in both directions. So local behavior, remember, we are interested in a local value of x, not an infinite value of x. So we see here that there's something interesting happening in the graph right there where x equals 3. So that is our area of interest, and there's actually an asymptote right here. So we are going to describe our local behavior using limit notation. So the limit of our function g of x as x approaches 3. So first we'll talk about it from the right. So as x approaches 3 from the right side of 3, we can see that our function is approaching infinity. So it's going to go up forever, and then we talk about the limit as x approaches, whoops, I forgot to write my little plus sign. So don't forget that plus sign. That indicates from the right-hand side of 3. As x approaches 3 from the left side of 3, we can see that the function is doing just the opposite. It's going down infinitely. So that limit at negative, or at 3 from the left, is negative infinity. And then our vertical asymptote, we have already specified. That is right here at 3. So again, vertical lines occur at a specific x value. So the equation is x equals 3. That's the equation for our vertical asymptote. So I just want to draw your attention to the fact that this vertical asymptote, just think about how we could have predicted that without having looked at a graph. So if you look at our original equation for our function, where would x equals 3 show up in our original? And I'm hoping that you're noticing that because the denominator is x minus 3, and we know denominators cannot equal 0, x minus 3 can never be 0. It would be undefined there, which means x cannot equal 3, which is true because there's no function value when x equals 3. It's undefined there. There's behavior of the function very, very close to 3, but there's no actual point on the function for x equals 3. So you're going to see that this denominator is always going to lead us to what that vertical asymptote might be if there is one. All right, so this next example, I would encourage you to pause the video, try it on your own. Just make sure that you are getting used to using limit notation, just practicing writing it in the correct format, and that you're understanding how to, especially at the local behavior. So I would encourage you to pause, sketch the graph, and just quickly run through these. It's very similar to the one before, just to make sure that you're using the notation correctly and understanding. Okay, so if you went ahead and paused it and tried this one on your own, you can compare your work to this. So you should have graphed something similar to this and seen that the ends of the function, regardless of either in the positive or negative direction, were both approaching the value of 2. So the limit of h of x as x approaches positive or negative infinity is 2. The local behavior that we're interested in occurs at x equals negative 1. So when you're talking about local behavior, in this case with limit notation, it looks a little funky because you have the limit of h of x as x approaches negative 1 from the right. So you have a negative 1 and then a plus, or negative 1 and then a little minus. So it looks funny, but again, this little plus and minus just indicate from the right and from the left. So you see from the right the function approaches infinity, and from the left it approaches negative infinity. And then that vertical asymptote at x equals negative 1, again, we should have been able to predict that from the equation. In the denominator we have x plus 1, which means x cannot equal negative 1, which is why there's a vertical asymptote at negative 1. Okay, so we're going to elaborate a little bit on these discontinuities that we're seeing in our graphs and how we can find those in the equation. So right now, in the past few examples, we've only seen these discontinuities that happen at vertical asymptotes, and we're going to look at as well on the next page. So there's two different types of discontinuities that we have to pay attention to with rational functions, and a discontinuity is any break in the graph. So it could be an asymptote or it could be a hole. And we're going to look at those two different things. The first type of discontinuity is called an essential discontinuity. It's considered essential because there's no way around it. There's no getting rid of an essential discontinuity. So it can't be removed. There's just going to be a discontinuity there. And we've already been looking at these. These are the vertical asymptotes. So now when I say essential discontinuity, I'm hoping that you'll just relate that to a vertical asymptote. And we've actually already talked about where those appear, and that would be in the denominator of the rational function. But there's also removable discontinuities, and those are discontinuities that basically you could fill in by defining a new value of x, defining the function at a specific value of x. So a discontinuity that's removable we refer to as a hole, because there's just a single point where the discontinuity occurs rather than an entire vertical asymptote where the function literally can never touch. So a discontinuity that you can fill in that's removable is a hole. So when we're looking for those two discontinuities in the equation itself, what we're looking at, the first thing you're always going to want to do is factor the equation as much as you can. Once you factor it, you're going to see that some of the factors may cancel. So when we see x plus 4, that simplifies our expression to this, but that should still raise a red flag because x still cannot equal -4 even though you cancel out those two factors. So any x value that you remove from the equation itself by canceling from the denominator, that still is going to be a discontinuity. So there's still a discontinuity at x equals 4, but it's removable, meaning it's a hole. So there's a removable discontinuity at x equals -4. And then if you look at this factor, x minus 3, there's nothing that cancels out within the numerator. That would be the vertical asymptote that we've seen in the past few examples. So there's an essential discontinuity at x equals 3, and that's a vertical asymptote. Vertical asymptote. So again, we've got two main types of discontinuities removable, which are holes. Those will cancel out, but there's still a hole there, even though we cancel them out from the equation. Essential discontinuities or vertical asymptotes are those factors that will not cancel out. So there's no way of getting rid of that discontinuity. So in this next example, we're going to figure out as much as we can about the graph before we actually graph it. So there's a lot of information that we can gather just by looking at that. So what discontinuities are there and where do they occur? So we always are going to look to the denominator for that. We see x minus 4. Now there's no other x minus 4 here, which means I can't cancel this out. There's no way around the discontinuity there. So that is an essential discontinuity. And that occurs at x equals 4. So that means we've got a vertical asymptote at x equals 4, which this is asking for an equation of any asymptotes that we have. So I'm just going to go ahead and fill that in because that's also x equals 4. So even though I'm not going to sketch the actual graph yet, I can at least anticipate this asymptote right here. Okay, so now we want to plot points for intercepts. So this is going to be a little bit of a review that you may need to review. To find the intercepts, the x-intercept or y-intercept, I'm hoping this will ring a bell. But when you're interested in finding the x-intercept, then you're looking for x values that make the whole function equal 0, or f of x equal 0. So to find that, you just set y equal to 0 and solve. So essentially, we want to know in this whole thing, the y value, our y value is f of x, we want to know when this whole thing equals 0. So when does x minus 5 times x plus 3 times x plus 1 equals 0? Well, that's going to be when either or any of these three factors equals 0. So that would be when x equals 5, or -3, or -1. Those are all our x-intercepts. Again, that comes from where our function itself equals 0. That's the x-intercept. So I will plot those on my x-axis. So we've got x-intercepts at 5, -3, and -1. So I still don't know what this function is going to look like, but I know a little bit more information about it. The next is the y-intercept. To find the y-intercept, think about what the x value is on the y-axis. If there's a point on the y-axis, then the x hasn't moved left or right at all, so that would be when x equals 0. So basically we plug 0 in for x and figure out what the value of the function would be. So for y-intercepts, you plug 0 in for x, and we would get -5 times 3 times 1 divided by -4. So you end up with -15 over -4, or 15/4. 15/4, that's approximately, that is actually 3.75. So that's the y-intercept. So I know that my function will cross the y-axis about right there. So here's all the information we got. We haven't even touched our calculator, hopefully, to see what this function looks like, but we know a lot of information about it. We were able to plot these 4 points, and we know the asymptote. Ideally, we'd be able to graph or plot enough, find enough information that we can graph it. In this example, there's just not enough. So now that we have kind of like the shell of our function, you can take a second to graph it on your calculator and fill in the gaps that we're missing. So this function has a quadratic piece that goes like this, and this other piece over here that looks like that. So this is the graph of the function that we figured out all this information for. All right, in this last example, again, we've got a function. It's already factored for us. Typically, you just make sure you factor first if it's not factored for you. We see right away, you should see that you've got x plus 3 and x plus 3. So we've definitely got a discontinuity because I can cancel out those factors. That means I've got a removable discontinuity, or a hole, at x equals -3. So we've got a hole at x equals -3. Now we want to talk about the x-intercept. Remember, the x-intercept is where y equals 0. So basically I'm just setting this equal to 0. When does that equal 0? That occurs when either x equals 5 or -1. So I've got my x-intercepts there. My y-intercept, this is going to be when x equals 0. So that I would plug in 0 for x and get -5 times 1, which is just -5. So notice I didn't use this when I was finding the x-intercept. I could have put times -3 up here, divided by -3, but you'll see those -3's will just end up canceling anyway, and I still get -5. The equation of any asymptotes that we have, we do not have any asymptotes in this. We can definitely be sure there's no vertical asymptotes because we didn't have an essential discontinuity, so we actually just don't have that. So let's see what we can piece together from our graph or information so far. We talked about x-intercepts being 5 and -1. So let's say this is -1, 5-ish over here. And we've got a y-intercept at -5. So with these 3 points, we still don't know a whole lot about what this function will look like, but if you think about what will happen after we cancel out these 3's, really you've just got x minus 5 times x plus 1, which is a quadratic, and that's exactly what the graph does. If you graph it, on your calculator, you will see that you just end up with a parabola like this. And there's a hole in this parabola that you wouldn't notice on the graph, but there is a hole at x equals 3. So when x equals 3, the graph here, there's no break in it on your calculator, but there is a hole there unless you fill it in by defining the function where x equals 3. So I'm going to stop here. The main thing that you guys get from these notes is that you're able to look at a function and identify discontinuities, what type, essential or removable, and x and y intercepts of the graph. So those are the main things that you should walk away with being able to do and understand. And we'll finish these notes in class.